So last time, we kind of say that when we want to solve a two-level system, and then with the light interacting with the atom, we previously solve it like semi-classically, right? The atom is quantized, but not the electromagnetic field. So we kind of we simplify our case a little bit. We put the light inside a cavity so that we know how to write down the field. And then last time, I think Z. Okay, this is your E field. And then, by the way, in the cavity, the E field and the magnetic field is in the 90-degree phase shift. Okay, I leave a note in on the website, and then you can take a look at it. Okay, it's a little bit subtle about there's actually left-handed and right-handed. Okay, it's a little bit stupid, but this is a case. We might have time to talk about it if we finish early today. So the E T Z, we define it as along x direction, okay? And then because it's in the cavity, so you actually have knob, okay, sine kx. And then we give it an amplitude 8, sorry. And then we leave the rest of the time-dependent thing into a Q, right? Okay. And then we can, later we figure out A, if we define it in a way like it's 2m omega squared epsilon v. M is a mass, like imaginary mass for the photon. Omega is light frequency. V is the mole volume of your light inside the cavity. And then we can write down the Hamiltonian of the light as so the Hamiltonian of the light will be identical to a harmonic oscillator. And the reason we go this path is because people have solved harmonic oscillator before. They know that the eigenstate of a harmonic oscillator, okay, eigenstate function is right. So this is the energy of one photon, and then it's recording. And then n is the number of state. It's like how many photons you have in your system. And of course, this, mathematically you can actually solve the eigenstate as a function of Q. Okay. Very complicated function. We talked about it last time. And I think also here we want to define momentum is, right, just like normal. Momentum is, m times speed, okay? And last time we mentioned that the difficulty was mathematically solving this equation is kind of exciting because you already got like the energy of one photon. But the problem is you can't write down E. Right? You can't write down E because E is a function of Q. And here there's only a wave function of Q. So it's like you need an inverse function to write down E. And then to solve this, we kind of propose an idea that if there's an operator, when you hit it on n photon state, you end up with n plus 1 photon. And the argument is this process is associated with absorption, well, with emission in the photon and light, light and matter interaction, right? So emission, you get one more photon. And then also you have absorption. Okay. You have absorption. You reduce the photon in your system by 1. So this is our guess. We think, well, if we can find an operator like this, it will be helpful to solve this light and matter interaction problem. And also we make another guess of what the A is. It's a linear combination of X and P. Okay. And then we can plug this, well, here X and P is. Right, because this equation is the same, Hamiltonian is the same as harmonic oscillator, so Q and X, you can replace them. Okay. So what else did we do is that we express X and P in terms of A and A dagger. We put it back into the Hamiltonian, and the Hamiltonian would look like this. Okay, so this is where we stopped last time. And then now starting from here, it's a little bit really quantum mechanical here. Okay, so by defining A and A dagger and then derive the Hamiltonian from this equation, again we didn't use any quantum mechanics, right? It's just linear algebra. Okay, so simply by doing this, you won't get a quantum mechanical result. Okay, previously the way we get here is by using the Schrodinger equation. Okay. Schrodinger equation solves the eigenstate. And if we kind of repeat the same route, then you can see you have to replace A with X again, and then you have to repeat, all of this result. So it's kind of a dead end if you try to go from here to here and then solve something. Okay. So the one thing that's we want to add to this equation is commuter. Okay, commuter is proposed by by Heisenberg. So it's in the early 1920s, and then Schrodinger kind of discovered the wave equation, wave nature of quantum mechanics, and Heisenberg took a very different route. He saw that he saw this. This is a little bit counterintuitive. How come you first get your momentum and then get your position? It's different from first get your position and second get your momentum. Okay, so this is counterintuitive, but he kind of assumed this. Well, we can derive this later. But he kind of assumed this. He kind of assumed this commuter thing, and then work out the entire quantum mechanics, and those are equivalent to Schrodinger equation. Okay, so Schrodinger equation is not it's not the only way to express quantum mechanics. It's just a very easy way to do it. So nowadays, people mainly use quantum mechanics instead of Heisenberg's method. Okay. So the idea of this is that whenever you measure something, you can think of it. You measure something, you actually change the state of that. Okay? And that's an intuitive way to understand. When you first measure x, you actually change the state. So that's why when you measure p, the momentum change. Okay? If you do it reversely, you first measure p and then something change and you measure x. So these two cannot commute. A more mathematical way to do it is to think of the wave function itself. How can you get momentum? Momentum we're defining as, right now here, is m dx dt. Okay, this thing is kind of annoying in your Schrodinger equation because first of all you don't know x, right? And then now you need to know dx dt. Kind of impossible to do. So momentum in wave function, there's another way to do it. Is proposed by de Broglie. So everything is a wave, theory. Okay. So everything is a wave. A wave must have a frequency, and then a wave also must have a wave vector. Okay. So this is the momentum he proposed for a wave. If you calculate it, it actually gives you the de Broglie wavelength. Okay. So momentum. Okay. So for a wave function, how do we get the momentum? Wave function always have propagating, and then to get the k, it's actually partial, right? You do a differential on x, give you ik. And then if you multiply h bar divided by I, h bar divided by I, get a p. You get a momentum. Any questions here? Okay. So you kind of just have to accept this. And then, so in this way, if you kind of are OK with this, now your momentum can be expressed as minus I, this part. Okay. Okay, this is your momentum. So whenever you try to calculate momentum of something, you do this, right? Average momentum. Do inner product and then do this. Okay. So this is actually very interesting because now momentum is an operator. It's a differential operator. And then we know that, well, if it's an operator, then you can't easily switch order unless they're independent operators, right? So think about this now. xp is minus I h bar x. Okay. Px is minus I h bar. So if you do try to calculate something, let's say you put a wave function here. These two does not equal to each other, right? When you do this differential, you have to use the chain rule. So this one gives you minus I h bar. First do the x, you get phi, and then you do the phi, you get right. It's off by minus I h bar. So we call this x and p not commute. Okay, this is commuter defined as xp minus px. And then if you plug this in, okay, RH bar. So xp and px is off by a very small number h bar. And that's why actually in classical physics, people kind of can't observe this effect because this is so small. Okay? And in quantum mechanics, it starts to show up. And if you don't understand it, it's fine. Just remember this. Okay? And then there's some kind of quiz. Well, I think if this is a quantum mechanics class, then that would be the homework. But we'll just go through those very quickly. Okay. So first, let's say we have a particle, and then this is x1, x2, x3, right? 3 axes. And then associated with it is p1, p2, p3. Okay. So the question would be, natural question would be, x1, p2, is it 0 or not? Always say, is it 0 or any guess? You have 50% chance of making the correct one. 0, okay. You're from physics department, I expect that. Otherwise, I would tell your advisor. Okay, 0. Yeah, it's because they're independent. You can think of it as what you do on the x-axis doesn't interfere with what you do on the y-axis. And it's not always true. Okay, it's not always true. If you're thinking about spin, x and y, z are kind of all mixed together. Okay, so for this, we always have xi pj minus h bar delta function. Okay, if they are equal, then you get minus ih bar. If they're not equal, you get 0. And then the second one is this Q here represents the mode, right? The electrical wave. In a cavity, there's many modes possible. You can write down a mode as omega j, kj, right? Its eigenfrequency and its wave vector kind of define your mode. So this associated give you qj, and then pj. Right? You do this. Yeah, you do this definition, and then you get qj and pj. Okay. And if you try to commute Q1 and P2, let's say there are 2 optical modes at different frequencies. Is this one 0? Yes? Okay. Some of you are saying yes. Okay. So this one is 0 in most cases when you don't have 2 light interacting with each other. Right? That's actually commonly true, because light and light interaction are usually very weak, and especially when we are considering like a field photon case. So this one is also usually 0. Okay. And yeah, I guess that's kind of it for the commuter. Like if you can understand this and then use it in calculation, then that's good enough. Okay, now let's do this. So here we already got A dagger A plus A dagger. And it would be great if we can knock out 1. Right? Then you only get 1 operator to worry about. Okay? So it would be natural to think about this, right? If it's 0, that means these two are equal to each other. You can knock out 1 and then add a 2 here, right? If they're not 0, maybe there's a number there, and then you also use that equation, plug in here, and then get a number. Okay. So A dagger, you just plug in this, and then let's do this here. Okay. Well, let's see result. Okay, the first one, A times A dagger. Remember, you can't switch X and P. Always follow the order. If you find X on the first and the P on the second, then write it in that order. Don't switch. Every time you switch, you create yourself a trouble. Okay. So first, this one and this one, you get m omega 2h bar squared. This and this, you get yourself 2mh bar omega 1. Okay. A dagger, okay, minus I, and then this times together is 2h bar x p, and then this times with this plus I. Okay, this is A dagger minus A dagger A. The first two are the same. All right, A dagger A, you have the same term here. And then the cross term, this one and this one, you have plus I 2h bar x p. Okay, and then this term minus I px. Okay, so these two cancels, and then what you left is minus I h bar. You have 2 here, so this 2, well, half is 1, and then you get xp minus px, right? Xp minus px is IH bar. Okay, it's 1. So this is kind of extremely beautiful. If you, well, we're only halfway here, but since this is 1, you can guess, well, you're making a very good decision in defining A and A dagger. Okay, it turns out very beautiful. And but actually you don't even need to calculate this because this is dimensionless. So this can be 0, minus 1, and 1. That's only 3 options. Maybe minus 2 and 2. Okay, the only 5 options you can have. And let's write it down as 1. Okay. So put this back to here. A dagger equals 1 plus A dagger A. Okay. plug this in, back in the Hamiltonian, and then what is this? Look at this too. Okay, they're almost identical. So now what we can do is we use something we know, okay, to kind of try to figure out the property of A dagger A. The thing we know is this equation, the eigenstate equation. When you hit Hamiltonian on an eigenstate, it gives you the energy of the eigenstate. Right? So when you hit Hamiltonian, when you hit your Hamiltonian on the eigenstate of n, it gives you this, right? Nothing fancy here, just plug into these two equations. And then you get the terms out and this out. And then what you get is A dagger A n equals n. Okay. Don't try to do this. Okay, don't try to do this. I heard a joke from a professor in UPenn, I think his physics department or engineering department, and he was teaching chemistry, and then he was constantly using this differential operator, and then at the end of the semester, undergrad came to him and say, "Professor, I want to be really polite, so I didn't say this during the entire class, but I think it's the end, I should tell you. Well, you should knock out this 2. So it's 1 over x. And it's right before the final exam, so and I think he missed his chance to drop that class. Okay. Yeah, so in quantum mechanics, you can't do that either. What it means is that when you hit A dagger A on a state, it gives you the number of that state. So this is an extremely useful operator. Think about it. You want to know what state you're at, like how many photons you have in your system. You just put this operator on, and then it gives you that number. Okay. And I think I need to restart the camera. So we actually call this number operator. Okay. Number operator is A dagger A. It gives you the number of photons in your cavity. Okay. And with this number operator, now it's possible to see our previous proposal, whether this is correct or not. Right? The idea is, well, you want to know if it really rises the number of photons by 1, then you put your number operator in the front and then see how many photons it has. And some of you might be afraid of, what about the normalization factor? Okay. The fact is, you don't have to worry about this, because if you are doing A dagger A, let's say on 2 phi n, okay, it gives you can move 2 in the front, then you get n times 2 phi n. Okay. So any state, even it's not normalized, you can still get the number of photons. Okay. So let's try this. Okay. A dagger phi n. And then we put number operator in the front. We want to know what it is. We want to calculate the number of photons for this state. And whenever you look at this and then you don't know what to do, there's only one rule. Do switch. Okay? Do switch. Switch this two. Right? Because you know A dagger A, but you don't know AA dagger on a state. So once you switch them, there will be something you know, you can calculate. Okay? So this is kind of the beauty of the of this operator thing. And also there's only limited options for you to switch. Right here there's only either this or that. Okay? If you try the first one, it doesn't work, you can do it again. Okay? So it doesn't matter. So when you try to do switch, then you have to use the this commuter relation. Okay. So A dagger equals 1 plus A dagger A. Okay. So what is this? This is n, right? Number operator. When you switch, the number operator show up. And then you hit on the n state. This gives you A n plus 1 . Okay. Always calculate the operator on the right first. Okay. And then you can pull out this number, so it becomes n plus 1. Okay, you see this? Number operator act on a state, give you n plus 1 times that state. So it means this state has n plus 1 photon in it. Okay. What it means to have n plus 1 photon, it means it's the same state as the n plus 1 photon state, right? There's n plus 1 photon here, so it's the same, but there's a coefficient in the front. There's a number in the front that, because this one only calculates the number of photon. It doesn't make sure that the normalization factor is 1. Okay? So there's a coefficient here. And you can kind of do the same thing for this one. Okay. A dagger A, number operator, act on this one. Okay. And then I'm not going to do it again, but the idea is to switch these two. Okay. Switch these two, and then you have a number operator here. And then you can do this. And you can show this is n plus, this is n, and then A. Okay, so this state only has n photon in it. So sometimes more often we write it down as this. N goes to n minus 1 state. Okay, so you lower the number in your system by 1. And to figure out to figure out the coefficient here, it's actually relatively simple. Okay, you do a Hermite conjunction, Hermite conjugate. So because this one, you know, this is orthonormal eigenstate, so you always have the inner product of them two are 1, right? You always have this. And then, well, let's do it. The inner product of n and m, right? If they're not the same state, the inner product is 0. If they're the same state, the inner product is 1. So what we can do is we can take this as an example here. Okay, we do the Hermite conjugate of this. You get, well, this is a little bit. Let's see. It's hard to. Well, I don't have a quick explanation why the right bracket become left bracket when you do the Hermite conjugate. Try to pretend just this is the way, okay? This is a Hermite conjugate of this, and then you times, okay. And then what will happen is, well, on this side, you also do this, right? The Hermite conjugate is C plus the conjugate. Right bracket become left bracket. Okay, and then times C plus 1. Okay, so this is C plus squared. Right, C plus is a number come out. And then the inner product of n plus 1 state and n plus 1 state is 1. Okay, so C plus the absolute amplitude of this. Okay, and again we come back to this one. Okay, whenever you don't know how to calculate it, you switch. So you switch and you get this. So this part, when you do switch, A dagger A plus 1, right? And A dagger A hit on this is n, right? Number operator on n photon state is n plus 1. Okay, the inner product of these two is 1. So you get okay. And there's many choices you can make of your coefficient, but the simplest one is to go with a positive real number. You can choose other bases, but yeah, I'm not sure if that will help you. Maybe in some very special case, that might simplify your calculation. Okay, we can do the same stuff for, so this one gives us A dagger n equals to, sorry. Right. So we now know what it is. So it's kind of magical. We know A dagger on n photon state indeed give you n plus 1 photon state. And also you can figure out the coefficient in the front. So mathematically, you can actually now use this with full confidence. You don't have to worry about coefficient or anything else. Okay. And then also, what is A? This one gives you, okay. So you can repeat the same calculation, same method here, but this will be the result you get. Okay. Let's see the next one we want to. So now we can return to our original quest, is to figure out what is electrical field in the quantum case. Okay, now the answer is quite pretty clear. You have Q. Q is the same as X. So Q is the same as X, and then X can be expressed as A and A dagger. And then you know what A and A dagger can do on your number of photon state. Okay. By the way, this is called Fock state. It's a number of photons is called Fock state, and often it's simplified to this. Okay. And actually, you can create Fock state. You can create the like single photon, 2 photons, 3 photons. You can actually do that. And then next class, we will actually talk about a very simple model. Photon, 2 energy level atom in a cavity that can create a photon number selecting device. Okay, you can kind of select how many photons can pass through your cavity. Either it's 1 photon, 2 photons, 3 photons. It's kind of a magical thing. And yes, so let's write it down here. We have S2. If you plug in Q is X. Okay, so these 2 equations, you add them together, you get 2m omega h bar. Sorry. Okay, you add these 2 together. 2 come up, and then A plus A dagger, and then you move this from the right-hand side to this side, so you get H divided by this. Okay, so this is your Q. So you plug that Q back into your E, your electrical field. Now you get your field. Okay, and A is 2m omega squared epsilon V, okay, times h bar 2m omega and you cancel out these terms. And what's left inside is h bar omega epsilon 0 V. Okay, A. So this is actually something useful now, because when you try to calculate, well, first of all, you know what E is in terms of a quantum operator. And also you know what this quantum operator will do when you apply E on a state, right? So you can actually start to use this to calculate a lot of stuff. Okay? And so now we can erase all this. we make a summarize. This will be the things you guys would use. Ex. Yes, let's do it. Later you will see this part. This part is actually the amplitude of vacuum, electrical field of vacuum. It's actually not zero, so that's one quantum effect you will have. Okay, and we know the light is doing oscillation, right? Cosine omega t, right? And this oscillation is actually hidden in here because I just erased it. We kind of throw all the time-dependent thing into x, right? So it's actually, you can prove it. You can actually prove it here. You can do sometimes, most cases you can pull out the time oscillation term, okay, because it's just a number doing oscillation. You can do this. And it really depends on what you're trying to calculate. It's perfectly okay if you don't pull this out. You will see this term later when you try to calculate the dynamic equation of these operators. And then you have, and then in free space, this is cavity. Okay, and then there's a free space. Okay. So the free space, the idea is to expand the L, the length of the cavity, to infinity. And then what will happen is, I think this part you can look it up in Wikipedia. It's a little bit mathematical, but the result is actually make a lot of sense. So we just skip all the math part. Okay, so this is the electrical field of a light in free space when you do when you write down in a quantum mechanical way. And you always have A equals 1. Yes?
So if we're in free space, V was the volume of our box?
Yeah.
What is volume in free space?
So it's actually infinity. Okay, it's actually infinity. The truth is, no one actually do experiment like receiving light from minus infinity to infinity. They always, let's say you generate a light from a really big laser, then you still have kind of a volume there. Okay, so so in reality, this never goes to zero. This never goes to infinity. Okay.
So in the vacuum electric field, this amplitude is dependent on the size of our experiment?
Right, yes.
Okay.
Yes, and think about it in this way. So zero photon has this energy, right? And then the energy is integration of your energy density over this volume equals this. So the larger your cavity is, the smaller your vacuum field is. Okay. So in experiment, so this is actually one. This is actually a very good question. So nowadays, the field, I think it's 20 years ago, the field has already evolved into a stage that you can have a single photon interact with a single atom. And one of the trick is actually to make the cavity really small, so that the field of a single photon, or even a vacuum photon, the field of a vacuum is large enough to alter your atom. So one interesting fact, I think, since we're talking about this, is let's consider a case. Atom is in here, and then you have one photon. Okay. And then when this atom absorbs that photon, there will be no photon left. So if we're thinking about it in a classical way, since you have no photon, you have no E field, the atom should stay there forever. Okay. But the fact is, the photon is actually, well, the atom is actually doing, this is ground state, this is excited state. Okay. The vacuum electrical field will actually pull this photon down. Okay. So it's a little bit hard to imagine, but later in the later after we finish this next class, we'll actually talk about this. So this is something, well, kind of a proof of the vacuum state does have influence on your system. Okay. And yes.
Does it eventually decay back to the ground?
Yes, if you consider the energy dissipation. So that's again a very good question. So the second thing people are working on, well, has been working on for like many decades. One is to make the cavity really small. The other is to make the loss really small as well. Okay. So I think it's 10 years ago. There's a collaboration between Jeff Kimball and then my advisor. And what they do is they cool this atom like to almost zero temperature, and then there's very little decay of the atom itself. And also the cavity, they make it really good. The lifetime of the cavity is 1 microsecond. So the photon can be trapped inside for 1 microsecond, and that corresponds to photon traveling 300 meters. Okay. So you can do a lot of bounce, in one photon lifetime, and then that's kind of the way they observe this. They kind of do this and then slowly decay back to the ground state. Okay. And it's still a very exciting area, because this is, you can think of it as a foundation of how you transmit quantum information. So the information transmitted is just like classical information. You should do it with photon, because travel with the speed of light, and there's so little absorption in fiber. And yeah, so having a single photon here interacting with something, well, the atom, you can think of it as, it can be a gate, right? It's in the upper state or lower state, it will have a different effect on you. Just think about this. If you have photon input and it's in the lower state, what will happen is this might absorb the photon. Okay. What if it's in the upper state? It cannot absorb the photon, and the photon will pass. It's actually much more complicated than this, but you can think of it, the atom, you can use atom to control the photon. And also you can do the reverse. You can use the number of photons to control the atom. Okay. So back on this, we have cavity, free space. You need this operator. And then also you need to know this. Okay, so this is kind of all you need. After you quantize the electrical field, quantize your light, you just use this E. Let's say, for example, you have, previously we have, our Hamiltonian of this two energy level system, we have a term, let's see, Q, X, E. So this X is really a position. It's not the same X there. Okay. So you just plug in this one to here, and then you finish your quantization. Of course, you need to cancel out some terms. Some of them violate energy conservation, but this is how you use it. And let's see. And now let's see something. Well, let's try to calculate something interesting with these operators. So the first thing we want to see is, in vacuum, the electrical field is not zero. Okay, we'll kind of think a lot about this in this class, but finally right now we can actually calculate it because we can write down E as a quantum mechanical operators. So how can you do that? So the field is, well, the state is 0 photon state. Okay? And then we say that when you try to calculate the average value of something in quantum mechanics, what you do is you do an inner product of this state, right? You do an inner product of it. And can anyone guess what the result of this is? Make a simple argument, and then we can save some time to do a calculation. Any guess? You know, it's interesting, like, it actually happens in my, well, in China the system is a little bit different. We don't have SAT, but we have multiple ways to get into college. One is to enter a physics Olympic exam, okay, competition. So in the last question of that exam, it's kind of quite advanced. It's asked you to calculate the mass of neutrino, okay? I don't know what neutron is. I was just 18 years old. And then I somehow got my equation wrong. When I look at it, I couldn't see a solution. Okay? The only possible solution is if there is something 0, then left-hand side equals right-hand side. And so I write down the answer, the mass is 0. And it turns out it's correct. And I got admitted. So sometimes these things can really help you. So the answer is 0. Right, because you're having direction. You can have you can have upside, downside. So on average it's 0. Okay, just that simple. It doesn't matter what state you're in. Okay, even like n photon state is still 0. Okay, and then yeah, the average value is always 0. And then the next thing we want to know is, well, since this is 0, what about the average value of its square? Okay. If the square is 0, then this thing might really be 0, right? The square eliminates the positive and negative. It's always positive. So you write it down. This we assume we're at the maximum position. Okay. So we have E squared. Okay, we have this, and then let's first ignore this. You can show that they cancel out. Okay, when you calculate it. Just let's ignore those oscillation terms, and what you have is 0, E squared. E squared is A knob square plus A plus square plus A knob A plus A dagger A. Okay. And then, so to calculate this, well, the reason I said this is, well, we can ignore this is because when you calculate these two terms, these two numbers cancel each other, right? A dagger A and A dagger A and A dagger. When you calculate these two terms, because these two terms are 0 actually, the reason is you just do this calculation using the property of this is creation operator and annihilation operator, right? So say A dagger square A hit twice. When you hit one, you get rise the number by 1, and then you rise again, get to okay, and then let's the inner product of two state with different photon number is 0. So you go to 0. Okay. The same apply to this. So this thing goes to h bar omega epsilon b okay. So again, you do the same thing, right? This is number operator. This one is easier. This one is number operator. Number operator act on 0 is 0. So this term is 0. And what about this? It rises to from 0 state to 1. Okay. And then this act on this, it lower the 1 state back to 0. Okay, we can calculate this a little bit. Okay, what will happen is you first use this, n plus 1, so it's 1. Okay. And then when you calculate this, you use this. Oh. Sorry about this. Okay. You use this, and okay. So this term act on 0 state, give you 0 state. Well, at first, you might find this like creation and annihilation operator kind of difficult to understand, and also you might find it weird that, well, since when does my electrical field become an operator? Okay, but once you calculate enough things, well, a lot of things you find them very, very useful, and then the calculation is like middle school level, the math. So a lot of cases that you won't even return, you won't even go back to the classical case, yeah, just because it's so easy to use. And so this is 0 state. This one, this one is 0 state. This one is absolute 0. So what we now get is bar omega. Okay, and then the inner product of a state is 1. So you have this. Okay. So square of the electrical field of a vacuum state is not 0. Okay, your vacuum has something in it. And well, some people will actually well, let's finish this and then later go back. So from here you can see the vacuum state, the magnitude of the electrical field of your vacuum state will equal to this. Right, this is square. You make a square root. Okay. So this is often referred as the electrical field of a vacuum state. And of course, you can try to calculate this. Okay. I think you will find that when you add a photon to a state, this place simply add an n. Okay, so every time you 2n or n. So this also kind of represent the electrical field intensity or the amplitude of your electrical field of one photon. Okay, of one photon. So let's say now if we want to try to understand this problem, you have two energy atom in a cavity. Okay. Now you can estimate what will happen if you have one photon. Then you get your E field is this. Okay, this is a very small number, right? This is EV level, and then you have to divide it by the mole volume. And we previously know that there's a Rabi frequency of our system, right? If you have two energy level, and then you have an electrical field coming in, your atom would do oscillation from ground state to upper state back to ground state, and this will have a E inside. Okay, remember this. Something like this. And then now you can plug it in. You can kind of estimate how long it would take for a single atom to move from ground state to upper state. Okay, you don't even have to calculate the full solution of your, using quantum mechanics. You can just estimate. This is one thing. The other thing is going back to the free space question. Okay. So for a cavity, we know we have to satisfy the periodic boundary condition. Okay, so it's like after one round trip, the phase change has to be 2 pi, multiple times of 2 pi. What that also means is your wavelength lambda times integer equals the round trip time, round trip distance. Okay, and that means you actually have a lot of different mode inside your cavity, right? Each lambda m goes to omega m. Okay, so in a cavity, sometimes we will write it down as, let's see, we'll write the E as a sum of M mode. Okay, of M mode. Now there's really a problem showing up here now. Okay, so for each mode, there's half a photon energy there, even you're in vacuum. Right. So this cavity here if you calculate the vacuum energy, it actually doesn't converge. It's explode, because you have infinite number of mode, assuming this is a perfect mirror. Okay, the reality is the mirror is not perfect, so there's a cutoff wavelength, so there's a limited amount of energy you can have inside this. Okay, but if you have perfect mirror, then this thing will not converge, and then you have infinite energy inside your cavity. And so some people actually took this argument and say, well, in free space, it's kind of the same thing. Okay, you have a lot of mode because your L is really large. Okay, so you can fit more M inside. And you have infinite amount of mode, so you actually have some energy in your free space, 0-point energy in your free space. 0 point means vacuum. And people are actually wondering if this energy is actually dark matter or dark energy. Okay, and I think you can make a theoretical argument, but the fact would be until someone observes dark matter or dark energy, you can't say yes or no. Well, unless you show the theory is not self-consistent. Okay, it will calculate something doesn't make sense. That in that way you can disprove it. I think right now it's still kind of in a debate. And one interesting fact is that Quinn Song and I, and probably Joe Campbell, we actually have a small project to detect dark matter. And it sounds a little bit crazy, and then I don't have high hope for that. I just hope that project doesn't destroy my reputation. Okay, so I'm actually expecting it to be a negative result. Okay, I don't want to be the person say I saw dark matter, and then some people show me, oh, you just saw a noise. Okay, so but this is something that, well, yeah, this quantum thing is kind of I would say interesting. It leads to a lot of new phenomenon. And then one story I can tell in 1 minute is that when Dirac, some of you might have heard of Dirac write down the Dirac equation, what he found is that their solution has two things. One is, well, there's an energy positive solution and then an energy negative solution. Okay, and you might think that's wrong. But actually, it's not wrong. Later, people find out antimatter, and that's associated with this solution. So there's a possibility that this 0-point energy is really associated with something, not just to interact your atom, but something might be a real matter there. Okay, and that's all for today. Okay.